Thanks. Thanks very much for everyone for inviting me here today and also coming to this talk. So what I'm going to talk about now is kind of very closely related to what Dan was talking about this morning, so it's still keeping with the steepest descent theme. And in fact, the motivation for this, the method I'm going to talk about right now, came out of Pathfinder. We were originally using Pathfinder for a problem, and then we decided we were kind of having to really shoehorn it into solving that problem, and perhaps it would be better just to create a separate piece of code or separate quadrature rule which would work well for the particular problem we had in mind, because it was quite a specific problem. I'll talk more about the specific problem at the end. It was kind of solving typically tens of thousands of highly oscillatory and singular integrals, hence the title, as part of a boundary element method. But I'm not expecting everyone here to be familiar with that. So instead, for the motivation, I'm just going to consider the Hankel function, which is should be all the motivation you need, really, because this arises a lot in scattering problems in particular, because it's the fundamental solution to the Helmholtz equation in 2 dimensions. Why is it interesting and why is it relevant? Well, hopefully you can see there's a singularity here, so it's singular at the origin, but also, so for small argument, yes, we have this logarithmic style singularity, and for large arguments, actually, shall I use the stick? Yeah, it's better. Actually, I'll need one in each hand, I think. And for large arguments, it oscillates. And obviously, as we'll see later on, we're interested in the case where this oscillates a lot. Okay. So in particular in this talk today, I'm going to start by talking about generalized Gaussian quadrature, because this is my method of choice for singular integrals. It's perfect if you know enough information about the nature of your singularity. Then I'm going to just quickly recap steepest descent and how we use this for oscillatory integrals. Then I'm going to combine the two, which is actually quite straightforward and a very natural way to extend steepest descent to the case when you have singular integrals. I'll give a few kind of derivations of error estimates. And then finally, I'll get back to this application that I mentioned, which was kind of the motivation for all of this in the first place. Okay, so throughout the talk, I'll be referring to this kind of model integral. So I'm just going to assume, for simplicity, that the singularity is a logarithmic singularity. This can easily be generalized to algebraic singularities as well. I'm going to assume that f is non-oscillatory and non-singular. So effectively, what I mean by that is it's well approximated by a polynomial. I'm also going to assume that k is large, and this beta parameter effectively relates the oscillations to the localization of the singularity. So because our k is large, the logarithmic singularity does also depend on k here. T0 is effectively the position of the singularity, but somewhere perhaps close to 0, but slightly below it. Oh, and I've adopted this festive formatting. So throughout the talk, red will mean oscillatory and green will mean singular. I apologize to anyone in the audience who is colorblind. Also, to anyone who doesn't celebrate Christmas as well, I apologize to you all. Okay, so singular integrals. A very kind of one way to interpret generalized Gaussian quadrature is to kind of reformulate the problem for regular Gaussian quadrature by imagining that you're solving a 2n-dimensional nonlinear square system, and the solution to this system is your nodes and weights kind of bolted together in a vector. So, and classical Gaussian quadrature satisfies, well, this is effectively how you would write down your nonlinear systems. Nonlinear, of course, because we have increasing powers of x here. So p effectively is the degree of the monomials for which we want the Gaussian quadrature rule to be exact. You wouldn't solve this by kind of thinking about this in this way. There are much nicer ways to solve this problem, but in the case of generalized Gaussian quadrature, this is kind of the most sensible way to think about it. So just to kind of, let's do a quick comparison between the two. Gaussian quadrature, we have this 2n-1 exactness, so we're effectively saying for polynomials, or in this case, the way we formulated it, monomials, we want this to be exact for degree of up to 2n-1. But in generalized Gaussian quadrature, we're effectively sacrificing some of this exactness in exchange for also gaining exactness when we have the monomial multiplied by the singular function. In this case, it's the logarithm. Okay, and because we have 2n unknowns, we instead here we ask for, rather than 2n minus 1 exactness for the monomials, just n minus 1 exactness. But we also ask for n minus 1 exactness for the log times monomial. So effectively, generalized Gaussian quadrature is great for functions which are well approximated by a polynomial plus log times functions which are well approximated by a polynomial. Yes, so that's just a quick overview of generalized Gaussian quadrature. Just to see how we might apply it to our integral in the case where we've chosen beta equal to 0, which effectively is rendering this non-oscillatory because the oscillatory term will be killed off. So it's this simple. But we do have this frequency parameter inside of the log, but just using elementary stuff we know about logs from school, we can split this integral up. So effectively what we've got here is now log times something well approximated by polynomial plus constant times the same thing again. So what's nice about this is although generating the weights and nodes for a generalized Gaussian quadrature rule is difficult, it's a non-trivial task, I would say, and still an ongoing area of research. Once we have them, we can use them for any value of k, which will become useful later on. And in the same way that here we've effectively generalized Gauss-Legendre quadrature, or here I would say, we could generalize Gauss-Laguerre. Now, if you think back to Daan's talk earlier, Gauss-Laguerre was the quadrature rule we were using along the steepest descent paths. So this is why we're particularly interested in generalizing it. So this is regular Gauss-Laguerre, generalized Gauss-Laguerre. Okay. Now just a recap of oscillatory integrals and how we deal with them using numerical steepest descent. So the pathfinder that was presented in Daan's talk this morning, I guess that's kind of trying to deal with a broad class of problems very robustly. I really should have said this in the introduction, actually. Trying to deal with a broad class of problems very robustly, whereas now the focus is kind of dealing with a very specific set of problems, but very efficiently. That's what we're aiming to do here. But the idea behind it is the same. We have an oscillatory integral here. Let's forget about the logarithmic singularity for the moment. Let's pretend it's just oscillatory. And the idea is to deform into the complex plane. And by doing this, we're swapping our oscillations for exponential decay. So our integral is initially from 0 to 1 along this line here. Extend a little into the complex plane. And now we have an integral up here, which is this guy. And then some kind of joining path here, which typically in applications you wouldn't compute this because it's oscillatory, but you know that it's exponentially small, so you can ignore it as long as p and k are sufficiently large. And then this integral here corresponds to this path here in the complex plane. In the case where f is just analytic in some neighborhood of the real line, p will be finite, but if f is an entire function, then you can take p to be as large as you like, and these integrals become infinite. And we can then group these together and use Gauss-Laguerre quadrature, which is perfect for integrals which have a weight function that looks like this, to evaluate this integral. And effectively what we've done is we've swapped this exponential, this oscillating exponential, for something with exponential decay, which is much more amenable to numerical integration. Okay, so now I'm going to aim to combine oscillatory and singular approaches into one which works for both. Okay, so this is the model integral that I started with, except we're specifying that the singularity is now at 0. So logarithmic singularity at 0. This is our original path that we're taking in the complex plane from 0 to 1. Okay, and the idea is the same as on the previous slide. The singularity is at 0, but in the interior of this region in the complex plane, we're still analytic. However, now we have an infinite contour here, for which we are singular at 0. And all we have to do is just use generalized Gauss-Laguerre. So this came up a few slides ago. So generalized Gauss-Laguerre is perfect for logarithm times smooth times exponential decay integrand. And then in the case of this integral, we just use Gauss-Laguerre, which is the same as in regular numerical steepest descent. Okay, so hopefully that's clear up to this point. If we were, for example, to deal with a near singularity rather than full singularity, so the singularity is just slightly behind 0 here, the process is similar. We're only interested, because we have, we're only interested in the case where the singularity is within, or is within the order of one wavelength from 0. Okay, and I'll explain a little bit more about why that is later on. So we know that this distance here is going to be less than or roughly one wavelength. So we can effectively assume that the integral along this path is non-oscillatory. So what we do is we use generalized Gauss-Legendre along this path, which is perfect for logarithmic singularity and no oscillations. And then it's the same as on the previous slide. Along this path, we have generalized Gauss-Legendre, which handles the logarithmic singularity and converts the oscillations into exponential decay. And then this path, which is, again, standard numerical steepest descent. And I should point out at this point that the fully singular case on the previous slide is really just a special case of the nearly singular case that I'm talking about on this slide, where t0 is equal to 0, this integral will vanish. Okay. Why is this fast in practice? Okay, so I've slightly generalized the integral now, so it's going to t rather than to 1. It requires only computation of just 4 endpoint quadrature rules. So we have Gauss-Legendre, 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 and their generalizations which handle the case of logarithmic singularity. So effectively, quadrature rules which work well for these 4 cases. Computation of these is difficult, but it can be done, and only needs to be done once. And then once that's been done, each of these can be rescaled for and just combined and pieced together for any value of beta, k, or t0. So for any near singularity, full singularities, high frequencies, low frequencies, it's very easy to construct a quadrature rule from these. So there's no need to compute moments. There's no need to grade the integral. So a lot of the approaches I've seen that deal with oscillatory and singular integrals, the approach they take is to grade towards a singularity and then just apply an oscillatory quadrature routine on each kind of each piece of graded mesh. But that's not needed here. So I'm not saying this is the best way to do it, but it works well in the application that we use it for. And I'll say it sounds like I'm selling you something. There's no hidden computational costs here. Okay. In terms of deriving error estimates, the easiest way to do this is to just think about where standard NSD estimates come from. So recall that on every steepest descent path, we're using Gauss-Legendre quadrature. And we know that this is exact for polynomials of up to degree 2n minus 1. And the estimates are derived from what is left over. So the idea is that you expand, you know that your integrand is going to be analytic, so you expand this as a locally convergent Taylor series. The first thing that doesn't get integrated exactly is going to be the 2nth term, or the term to the power 2n. Of course, this k comes from the change of variable, and so does this guy. Piecing all of this together, the error goes like k to the minus 2n minus 1 as k increases for fixed n. For singular integrands, the approach is very similar, but recall that now we're using generalized Gauss-Legendre rather than regular Gauss-Legendre, which has the polynomial, or the degree of exactness n minus 1. Following the same approach as here, we now get asymptotic estimate of, for fixed n, order k to the minus n minus 1 as k grows. Something that I should point out here is that in the case where you're dealing with a near singularity, you can still apply standard numerical steepest descent, and the error estimate will look the same. However, with steepest descent, the only estimates currently available to us are asymptotic estimates. The constant will be much larger in the case of a near singularity when you use standard numerical steepest descent to when you explicitly account for the singularity in the case of steepest descent when it's combined with generalized Gauss-Legendre. But there are no estimates to back this up. Suppose we're interested in more general paths. So rather than just the straight lines going up vertically in the complex plane, Suppose we have a more general oscillator, which, for simplicity's sake, I will assume has no stationary points in the interval of integration. So we can determine the steepest descent path from the singularity at 0. This is, again, assuming that f and g are analytic. It will follow that the steepest descent path is also analytic in terms of its parameterization. We also have the additional requirement that this new steepest descent path will not cross the branch cut from the logarithm. Okay. So the main idea, what I'm trying to do here is effectively just show that a very similar approach will work in this case, assuming that we have an explicit formula for the steepest descent path. And why is this? Well, it's because as long as the steepest descent path is analytic in terms of p, we can just rewrite log of k multiplied by the steepest descent path like this, which effectively just boils down to log of p, which we know will be singular at 0, plus something which is analytic. And we're in the exact same situation that we were on the previous slide, where we have a locally convergent Taylor expansion here and here. So as k gets large, the estimates from the previous slide will hold. Okay, now I'm going to talk more about the application, which was the motivation for all of this in the first place. But before I do, actually, I should say that we're particularly interested in applying this to the Hankel function, which was what I talked about on the motivating slide. And because we're trying to we're dealing with a practical implementation of this, we have to draw the line somewhere in terms of when something becomes oscillatory, when it's non-oscillatory, when it's singular, and when it's non-singular. Now, we choose our parameters to do this based on, well, the conditions for oscillatory is quite straightforward. It's just, is the integrand the width of the interval of integration? Is there a sufficiently large number of wavelengths along here? So, and that's what separates this split from this split. And here, the y-axis is the position of the singularity. 0 is fully singular, and then -1 is not very singular at all. And then the x-axis is the frequency, or sorry, the wave number, or k, and here, not very oscillatory, and here, oscillatory. What's interesting about this, and we found that the best way to do this was to actually choose this curve here to be a curve and not just a straight line. And what that means is that whether or not a near singularity is worth worrying about depends on whether or not your integral is oscillatory. To try and explain why this is, it's quite easy. If you just imagine the case when your integral is not oscillatory and you have a singularity, say, just outside of your, nearby singularity, just outside of the interval 0, 1. If you're approximating this kind of numerically, then you wouldn't be able to draw a very big Bernstein ellipse around your 0, 1 interval. This is going to be restricted by the position of the singularity, which is effectively going to mean that you will converge much slower. However, in the highly oscillatory case, as we saw in Dan's talk this morning, near the start of his talk, actually, we learned that most of the contribution to the integral comes from the endpoints of the integral. And this localization means that effectively, for sufficiently large frequencies, the nearby singularity can be ignored. And that's why this is a curve and not a straight line. Also, I should say, the main point of these plots is to actually just show that we can, with a relatively small number of quadrature points, we can get great accuracy across a large range of frequencies and location of singularities. Okay, so this is the scattering problem that we're interested in solving for our main application. So we have the Helmholtz equation, which I'm sure everyone here has met before, Dirichlet boundary conditions, and assume also that it satisfies some suitable radiation condition at infinity. We can reformulate this as an integral equation, which looks like this, where this is the Hankel function again. These square brackets around the normal derivative correspond to the difference in the trace taken from above and below the screen. And then the right-hand side is just based on known data, which corresponds to the trace of the incoming incident wave. Okay? One way to discretize this integral equation when we're at high frequencies is to incorporate kind of known solution behavior into the approximation space. So this is, yeah, so it looks a little bit like this. So these are kind of piecewise polynomials here in our basis, but we're approximating the unknown by exponentials times piecewise polynomials plus this term. Physically, this corresponds to the waves which are reflected by the screen, and we know this exactly. One way to solve this problem, or to approximate it, would be to use the collocation method, where we effectively are saying that we want the integral equation to hold at some number of points along the screen. We want it to be exact at those points. It will look like this. So these SM correspond to the points on the screen which we're forcing the integral equation to hold. This is nice because you can prove that we require the number of degrees of freedom to grow only like the logarithm of k, where k is the wave number in our Helmholtz equation. And in practice, it's actually better than this. For all the numerical experiments we've run, this is actually order 1. Whereas if you were to use a standard boundary element method, this would be order k. So this is a great improvement. I've put a smiley face there because that's good. Medium face here because we have order n logarithmically singular integrals. That's the same whether or not you're using a standard boundary element method. Sad face because when we're using this kind of hybridized approach, this trade-off is that you end up with order n squared oscillatory integrals, whereas in a standard boundary element method, you would choose your mesh width to be smaller than the wavelength of your problem, which means you don't get any oscillatory integrals, but your n is much larger. So it's a trade-off. So if you're going to take this approach and you want to have a fast method, you need something which can solve logarithmically singular and oscillatory integrals. But we have that, as we've seen throughout the talk. Okay, so just a few kind of results from the solver that we've made, which is available to download on my GitHub page, and also the preprint will be on the archive probably by the end of this month, hopefully. The error in terms of the number of degrees of freedom, as I said, it actually improves with the frequency k, which is the relative L1 error on the boundary. And the CPU time in seconds, so this is seconds to the power of a quarter, which is the situation in which we would expect flat lines, essentially because the number of degrees of freedom should go like the degree of the polynomial squared, and then because we square that again because it's a number of elements in our discrete system, each of these elements is an oscillatory integral. So that's why we would expect flat lines when the x-axis is CPU seconds to the quarter, which, yeah, I mean, they're pretty flat. But effectively, this is a very fast method, and for example, say 100 degrees of freedom, we're computing 10,000 integrals. All of these are highly oscillatory, and many of them are singular as well. So this method in practice works very well. Okay, so to summarize, numerical steepest descent can be applied to certain classes of singular integrals without the need for grading, provided that the relevant generalized Gaussian quadrature rule, or multiple rules possibly, exist. The steepest descent path doesn't cross the branch cut. And the resulting quadrature rules are then very easy and fast to compute once you have these generalized Gaussian quadrature rules. For future work in extensions of this, we're particularly interested in this generalization to this type of phase, so when, which obviously has 2 branch cuts in the complex plane. This is the case where rather than dealing with screens, we're dealing with polygonal scatterers. So that's our motivation for that. And also I should mention that all of the ideas in this talk can be extended to algebraic singularities of this form. That's the end. Thanks very much. Yeah?
So you spoke about collocation implementation. So if I want to do a Galerkian boundary element method instead, is the step up a dimension to a 2-dimensional oscillatory integral a nightmare, or is that?
I think it's doable, I think. Yes, but I mean, if you were to then deal with a 3D scattering problem, Galerkian, then you have 4-dimensional oscillatory integrals, which Dan once said should be banned by the UN. So I would say the 2-dimensional case is definitely achievable, and there are additional complications when you have 2-dimensional steepest descent. 4D, I wouldn't want to think about that because I'm much older. Yes?
So instead of using the generalized quadrature, would it be possible to add and subtract the singularity?
That's pretty much what we're doing, actually. Yeah. So we're integrating all the way to the singularity. Well, and that's so maybe you're talking about the non-oscillatory case. Yeah. So I didn't talk about that because there wasn't time, but in fact, yeah, in one of these quadrants, that's what's happening. So non-oscillatory, but singular. So down here in section 2, that's what's happening. We're going kind of from 0 back to the singularity, and then all the way to 1. And that's easier in practice, we found, than because the alternative would be to construct a new generalized Gaussian quadrature rule specifically for that near singularity if you wanted it to be efficient, or use standard Gaussian quadrature, which would converge really slowly. Yes?
So you deal with weak singularity, but if you have a Hschickernal, would you do it similar?
If I had a what, sorry?
A Hschickernal or Hilbert transform.
Oh, yeah. So it's not something I've thought about much. I think probably you would need a different approach. I don't know if, yeah, I haven't seen any. No. I think that you would need something different for that. Okay. Okay.
It would be better, in my opinion,